Good day, and welcome to Topic 7, Trigonometric Functions and Cyclical Graphs, Part 3, Equations of Sinusoidal Graphs. As mentioned at some point earlier in this whole topic, a sinusoidal function is one that is based on sine or cosine, some sort of transformation of one of those two parent functions. So when we transform it, we do have something that looks a little bit like this, or a and b are same as what we saw when we first looked at function transformations. And then the c and d kind of replace your h and k. In order to be able to determine the equation of a sinusoidal function, we're going to have to determine these things. We have seen a bit of determining a. If we can determine the amplitude of this function, we know that a value. We have seen a link between the value of b and the period. So if we can find the period, we can find the value of b. For d, we can play around with the range of this whole function. We know that a combination of the amplitude and this d value can give us the minimum or maximum value depending on how we combine them. And then finally for c, the shift or the phase shift as it's often called for sinusoidal functions, we'll have to decide whether we're playing with sine or cosine. So any of these graphs that we look at could be phrased either way as a function or the transformation of sine or a transformation of cosine. Maybe we'll be instructed as to which terms to put it in, or maybe we'll get to choose our own adventure, but we'll see. But that is the essential lowdown of what we're going to be playing with. It's that c value that I find can sometimes throw people off a little bit. When we look at the curve, we're always looking at some point on this, and this goes on forever and ever and ever and ever. It doesn't compress suddenly like that, but it does go on forever and ever. And really, we could be starting at any point on this graph. When we consider what happens normally for the y-intercept for sine and cosine, we can say that sine, with its graph looking kind of like this, starts in the middle. And what it does on the other side is that, right? And this continues this again, and then again, so on and so forth. So it starts right in this middling area and goes up. So by that logic, this point, or this point, or this point, those could all be starting points for sine. It's not necessarily the starting point, but we could use them to determine what's happening with our transformations. Similarly, when we look at the cosine function, we know that it's in terms of its y-intercept, it starts up here at 1, and then it goes down, up, and then here, and then it does it again, and then it does it again, and same on the other side. It keeps repeating that. Key thing is that it starts at the crest of this wave. So we could say that this point here is a starting point for cosine. This point here is a starting point for cosine. So when we're looking for that c value, that is what we're going to be after. And of course, once we have all four parameters, then we can write this equation of the function. So let's give it a try. So for each graph, we're going to provide the equation of the function based on cos x and an equation based on sine x. So in this case, we're looking for both, based on cos x and based on sine of x. So we begin. We did at some point have a formula for the amplitude. So if we can't just observe it and see it, then we can always say, oh, which page was it on? This, boom. That amplitude is max minus min divided by 2. So let's get this formulaically here. Scrolling on. Okay. Amplitude is A. A is max minus min, however you spell min these days, divided by 2. And looking at this function, we do have a max at 4. We have a min at negative 2. Therefore, A is 3. That is one parameter done. If that is all you get on this question, 1 out of 4. Good job. I mean, actually, I guess that's assuming that there are 4 parameters to find. However many parameters there are to find, you've gotten one of the marks for it. Now, we have to get, well, we can get these in any order we want. Personally, I would find the value of D next, right? Just finish off my vertical transformations. How am I going to find D? So, in my kind of side notes here, actually I'll do that in a different color, sorry. What I'm thinking to myself is that the range of this thing is from negative 2 to 4. So I've got a minimum which is equal to negative 2. I've got a maximum that's equal to 4. How do I get those based on the transformations? Well, my minimum would have been 1. Oops. Oh, great. But then we multiplied by A. And then we subtracted. No, what am I doing with my life? The minimum would have been negative 1. Then we multiplied by A. And then we added D. So, minimum is equal to A. Oops. Negative A plus D. Similarly, the maximum for a sinusoidal function is normally 1 when it's not transformed, but then we multiply by A and we add D. And we employ that vertical stretch or compression, and then we employ that vertical translation. So then our maximum becomes A plus D. From that, we can say, we can use either of these really. We can say that D, our upward shift or downward shift, is the result of taking the maximum and subtracting A. We could base it on the minimum as well. It doesn't really matter which way you go, but have some method of getting it. In this case, it's 4 minus whatever our A value was, 3. So it's 1. Next up would have to be B, our period. Purple. And in my notes to self, I know that the period is 2 pi over B. And I can manipulate this formula to isolate B instead. If I multiply both sides by B, PB equals 2 pi. And then to isolate B, divide both sides by P. So P, oops, yoink. B is 2 pi over P. And how on earth are we going to find the period of this thing? We can look at it a whole bunch of ways. We can look at the distance from crest to crest. We could also look at the distance from trough to trough. If it was indicated for us, which we can kind of see but don't really want to speculate here, we can go from that midline point to this midline point 2 over. So not the very next one, because that would be only half of a period because of how often it goes through there. But from one to one where they're kind of going in that same direction is what we want to play with. This one's going down. Ignore. Generally speaking, it's probably going to be easiest if you go from max to max, crest to crest, or from min to min, trough to trough. So if we look at this, from here all the way to here, we've got one period. We're going from pi over 2 to 5 pi over 2. So that whole distance is 4 pi over 2, which is just 2 pi. So I guess there hasn't been any horizontal stretch or compression. We can say it more formally. 2 pi over, well, 2 pi is what we found the period to be, so b is 1. Last thing is find that value of c, and we can do this a couple ways. So if we're basing things on sine, then we're dealing with those values. The sine function should be having its starting point on the y-axis, and instead it is, oh, actually still there, so we're okay. So based on sine, there's no horizontal shift, and we could just say y is 3 sine, what was b value? 1. So that's that. There's no horizontal shift, so there's no plus anything here. And plus our d value. Boom. If we want to base on cosine, we're looking at these peaks up here. Cosine should be starting over on the y-axis. Instead, it's starting at pi over 2. So we could say that based on cosine, we have shifted right by pi over 2. Therefore, its function will look almost exactly the same. Except now we're just going to throw a horizontal shift in there. And we're going to make sure it's to the right, so we subtract pi over 2. This one is done. That's that one. That's that one. Go ahead, try the next one on the next page, and then there's a wordy word problem on the page after that if you want to give that a go too. See what you can do before continuing this video. Really test it out. See where your skills at. Of course, I'm going to start. I'm going to be a little less explainy this time, so hopefully it goes a bit faster, because you, of course, have tried it on your own. My a value, max is 4, min is 0. That's that. My d value is max minus a, which is 4 minus 2. Boom. My period is something from here to here. Heck, let's just, wherever we want, really. That looks like it's 2 pi over 3, right? 'Cause this is 6 pi over 3. So period is 2 pi over 3. So my b value is 2 pi over the period, which is 2 pi over 3, which is 3. That's A, B, and D done. We just need everything, the c value based on sine and cosine. So based on sine, if we're looking at, this is our middle value. Based on sine, we could use that point, that point, that point, or that point, or this one over here for our starting point. So we could say there's been a leftward shift of pi over 6. And it's just halfway between 0 and negative pi over 3. Or you could even say that there's been a rightward shift of whatever this is. That's 3 pi over 3, so that's pi over 2. Either one works. So we can say 2 sine b was equal to 3 x. We can say plus pi over 6 if you want to deal with that leftward shift one, and plus 2 after. So that's valid. Or you can say this other one to give it a rightward shift of pi over 2. But that's all that changes between the two. And you can use these other ones as well, which we didn't use. Those would also be valid. And then based on cosine, looking for these peaks. One of them happens to be right on the y-axis, so we could say that there's been no horizontal shift. Oops. Hope I did the right function on those ones. Oh my gosh. Look at this. I wrote sine there too. My bad. Fix that. That'd be a real easy mistake to make. Your head gets into a certain space and then you think you're on a roll. Anyways. So this would be a good final answer. That one's based on cosine. These ones are based on sine. And again, there are other answers that you'll be able to get, right? We could use this as our starting point for cosine, or this, or this, or this. I happened to choose that one, but any of those 5 would work. A wordy word problem. How excite bike? So the London Eye, which happens to be, believe it or not, in London, is a large, slow-moving Ferris wheel that has a diameter of 120 meters. So this thing's a big ol' circly circle. And I guess that's 120 meters. The apparatus is mounted. Oh, because you don't want the bottom to be scraping the ground, right? If this is here, then that's going to be disastrous for the bottom of it. So apparently the bottom doesn't scrape the ground, so the passenger capsules reach a maximum height of 135 meters. So from the ground to the top is 135 meters. Good to know. One revolution takes 30 minutes. Determine an equation to model the height of a passenger capsule over time using a sinusoidal function in radians, assuming that at t equals 0, the capsule is at the minimum height. Oh, we can do this. Now, there's a lot of information that we can just process immediately. For example, we know that the maximum is 135 meters. The minimum is something, whatever height this is. How high is this off the ground? Well, this whole thing has a diameter of 120, but at its highest it's 135 meters above the ground. Then this piece here must be the additional 15 meters. So we can use that information. And boom, we've got A as the max minus the min over 2, which is, 120 over 2, so 60. Nice. We can also say that the period is 30 minutes. B is 2 pi over p. I don't need to write b again. 2 pi over 30, so pi over 15 if we reduce that to lowest terms. And I know how to write a 5. Nailed it, close enough. Well, we should also find the value of d at some point. I guess I could have gotten that. Sure, I'll do it over here. Max minus a, as we usually do. Yeah, maximum was 135. A was 60. So this is like 75. For finding the value of c, we're going to have to figure something out. Now, personally, I'll let you know, spoiler alert, I'm going to want to do this in terms of cosine, only because I know information about its maximum. I could also find out information about when it reaches this mid-height and it keeps going up, but I think it's easier for me to just find the maximum instead. When I look or picture graphically what's happening with the London Eye here, I know at t equals 0, we're over here at 15 meters up in the air. And then it goes up, and then it goes down, and then it goes up, and it keeps going along that path. And I know at some point it reaches this maximum. And that maximum has a height of something, 135. I know it reaches this bottom again at 30 minutes. Which means that it must be reaching this maximum at 15 minutes. So based on cosine, I can say that this thing has shifted 15 units. To the right. I could, if I want, also look at this point here, halfway between the min and the max here, and say that's at 7.5. So based on sine, we've shifted 7.5 units to the right. But why do the extra step when I don't have to? So if I were to put all of this together, so maybe in my little notes to self here, I know that I want y is equal to a cosine of bx minus c plus d, some form like that. Then, basing this on height and time, let's put appropriate variables here. The height will be, a value was 60. I'm using cosine. B value is pi over 15. Instead of x, let's use t for time. We have shifted 15 units to the right, so let's say minus 15. And then we've shifted upward by our d value, which is 75. And of course, if we're going to use these special variables, we should define them. It's very exciting, hence the exclamation mark. And that's how to do it. Now there is some practice work over here. We'll also go over a couple more of these in class, just see where you're at for determining the equations of sinusoidal functions. We'll mainly focus on non-contextual problems, I'll throw up a graph and ask you to find the equation of it, but we'll do some other ones as well, just for fansies, maybe some contextual ones. But try out this practice work over here. It's totes worthwhile because it's math, and all math is worthwhile. And if you have any questions, comments, concerns, please do let me know. Let me know in class or send me a message via Teams. I will miss you until I see you again. Tell everyone I say hello. Be good to one another. And keep making this world a better place. 'Cause that would be a good thing.